All right. Good morning slash good afternoon. Thank you all for coming and watching online. I know some folks are doing the live stream, so if you can just give me a thumbs up on the chat that you're able to get the feed, that would be super helpful. Meanwhile, I'll go ahead and continue. This is a guest lecture for a class at ETH, and I'm going to be talking about the phase field method, kind of in the context of solid mechanics and proposal writing. And so just a little bit about me. I'm a professor at Iowa State University. I do a lot of phase field modeling, computational modeling, and looking at solid fluid coupling, looking at energetic materials, microstructures, structural materials. So it's really fun for me to get to talk about this. Just a little bit of bookkeeping before we get started. I have one of my students is here in the room, and he's going to help me out with some of the technical aspects in case I miss the chat or anything like that. So. And also, we do have a YouTube live stream set up. So I know we have several folks joining remotely. And please feel free to stop me with questions. The virtual format is always difficult from an interactive point of view. Please feel free to stop me with questions. I think that helps keep the conversation ongoing. So, all right, great. Well, so phase field method is something I've been in for a little while, and I think phase field method is it's really cool because you can do so much with it. It's an extremely versatile framework, but at the same time, it's very theoretically sound. But at the same time, one of the things that I've noticed is that when people first encounter phase field, there tends to be this impression that the way to understand phase field is through this theoretical epiphany, that this truth comes down from the clouds and you have this amazing first principles understanding of all the physics in your problem. And to some extent that's true. A lot of the historical development of phase field does stem from theoretical development of Landau and Lifshitz, and that's very true. But at the same time, phase field is broader than just that. Phase field is a framework that allows you to do a wide variety of different kinds of physics. And so rather than this picture of understanding phase field, I prefer to think of phase field as a little bit more like this, where this is, if you've seen the movie Ratatouille, this is Remy the rat cooking in the kitchen, and he's just throwing all these things into a pot and stirring it until it smells and tastes about right. And while that's not all phase field is, I think that it is important to understand that sometimes when you are doing phase field modeling, there is a lot of intuition involved. There's a lot of intuition and kind of putting things together in the right way to see do these different pieces of physics drive the kind of mechanics or drive the kind of behavior that I'm looking for. And so this is a little bit like how I was, I think, when I first realized that a lot of these phase field models that you develop are actually pretty phenomenological. They're not necessarily derived, they're more constructed. I think that it's helpful to think about it that way because then you can kind of just suspend disbelief if you're not sure where something comes from, and just understand that we're going to try to understand it intuitively, and then see how to connect our physical intuition to a actual set of equations that govern our derived or our desired behavior. Okay. So I want to start off just by kind of going a little bit backwards. I want to start off by just giving you a basic phase field equation. And just some context, I'm kind of assuming here that everyone in the audience is maybe has seen phase field before, and you've kind of seen these equations around, but you don't really know where they come from, or how they're derived, or necessarily what they mean. So that's kind of the general baseline that I'm going with. I will assume that you have a basic level of familiarity with things like the variational derivative, or a variational calculus, or the Fourier transform, that sort of thing. So that's kind of the baseline that I'll be going with. But again, feel free to interrupt me in the chat at any time if you have any questions. And just so you know, there is about maybe a 10-second delay, maybe 20 seconds or so. It may take me a moment to catch up on when you send me the chat. So don't worry if it seems like I don't see your chat right away. Now, like I was saying, let's begin just with a phase field equation. So kind of a classic equation that you might have could look something like this: d eta dt is equal to minus L, and then we're going to have, let's say, alpha dw by dt minus 1/2 beta, and then the Laplacian of eta. Just a notational note, I'm pretty much always going to use eta to refer to an order parameter. I'm going to use the delta symbol to refer to the Laplacian. So this is del dot del. And I'm always going to assume that our domain is called omega. So that's going to be we'll try to keep the notation as consistent as possible. So what do we have here? We have a differential equation that relates the time derivative of eta to two different pieces. And let's start by understanding what this piece is. I'm going to first define w of eta, and I'm not even going to write it down. I'm just going to give you a picture of what eta might look like. So we might have something that looks like this, right? So this is a double well potential. We have a minimum here, we have a minimum here, we have an unstable point in the middle. We'll call this 0 and 1 for right now. Now, we take this derivative, the derivative of W, and we plug that into here, and that gives us our phase field equation. Okay, I think it's helpful to try to understand what do each of these individual pieces of our differential equation do for us. And to do that, let's begin by considering just a domain. So we'll call this our omega. We're going to consider a domain, and these points are all just randomly assigned between 0 and 1. Okay, so we've got all of our points here between 0 and 1, and so if we look at the distribution of points in our chemical potential, they're all kind of uniformly distributed over this interval. Now what happens if we consider only the first piece of our differential equation? So we're only going to look at this piece right here. d eta by dt is equal to minus L dw by d eta. Okay, so what this is telling us is that our d eta by dt, the direction in which our eta moves is going to be proportional to the negative of the slope of w. Well, that means that this point here is going to drift to 0, this point here is going to drift to 1, the points in the middle will eventually kind of drift to 0 or 1, but each point is going to pick which side it's going to move towards, and it's going to move in that direction. Okay, so now if we take this differential equation then and we animate it, so we actually solve it, we get something really boring. What we see is kind of what we had expected. Every point is kind of just moving either towards 1 or towards 0. And I apologize, it shall be red or blue. There should be no green. It's green because I used a nodal interpolation. Every point just moves exactly to 1 or to 0 because each point is moving on its own. It doesn't care at all about what the neighbor is doing. It's only caring about what it is doing. Okay? So if that's all we care about in our differential equation, then that is the kind of behavior that we get. We get this infinitely fine, high-resolution pattern of 1s and 0s. Now let's consider what happens if we look at the other piece of the equation. So this is the we'll call this the reaction portion of the differential equation. So I'm going to call this reaction. And over here, I'm going to call this the diffusion portion of the differential equation. So now we're only going to consider this piece here, and this may actually look pretty familiar to you because it's nothing other than the heat equation. Right? dA to dt is proportional to the Laplacian of eta. So it's a heat equation or a diffusion equation. And if we start off with our randomly assigned number at each point, well, what's going to happen? Well, it's going to be, again, pretty boring. The diffusion equation is going to smooth out as quickly as possible any perturbations. It's going to dampen this entire thing out, right? So, and we're going to end up there's actually an animation here. Just you only see it for a second because the transient is so slow, or the transient is so fast, but you see it immediately smooths out to this approximately equal to 0.5 solution. All right, so that's the diffusion piece, and we looked at the reaction piece. And so what I want you to think about is we have a differential equation that combines these two pieces together, right? The alpha piece, the reaction piece, is trying to drive the solution to that to either 0 or to 1. The diffusion piece is saying, I don't want there to be any sudden changes. I don't want sharp gradients to show up in my solution. And so what's cool is that when you apply these two competing mechanisms together, and you look at an entire phase field equation, you get this amazingly interesting and complicated differential or behavior where you get this curvature-driven flow that you may have seen before in demonstrations of phase field. And so what I want you to take away from this piece right here is that the fact that you get really interesting behavior in phase field is not a consequence of necessarily complexity. It's a consequence of the nonlinearity of our governing equations. And even a simple differential equation like this is able to produce this really interesting behavior. All right, now I started off just by kind of jumping right in and defining a kind of arbitrary phase field model. And now we're going to go back and look at actually how to systematically derive and work with differential phase field models. I'm going to just erase the board here. All right. So the talk, or this lecture is going to be 3 parts. I'm going to talk about theory, computation, and application. So, oh, and I forgot that I had another slide here. This slide, I just wanted to show that when you have your original differential equation, you have this piece here, and you have your alpha and your beta, that the weight of the two terms governs the long-term behavior of your solution. In this case, you have very fine behavior. In this case, you have very coarse behavior. And this is just derived from the balance between these two terms, the reaction term and the diffusion term. Okay. Now, let's start by talking about phase field theory. And you can easily fill an entire class with phase field theory and all the different variants of phase field theory and methods and computational applications. And I'm going to try to just distill the really interesting pieces and the maybe the more fundamental pieces into this lecture. So in the development of phase field theory, there are really, I think, of 3 main parts. The first part is the definition of the order parameter. The definition of the order parameter is how you define the kinematics of your system. It comes for free. You can pick whatever order parameter you want, and as long as you use it consistently throughout your theory, then it's fine. That's, again, the easy part. It's like the kinematics of your system. The way you connect this to physical reality is through the definition of your free energy. So using your order parameter, you're going to then construct a free energy functional. And then from that free energy functional, you need to know how to evolve your order parameter in a way that's consistent with its original definition. And so then you need a kinetic relation. So we're going to talk about all 3 of those, starting with the order parameter. Okay, so there's lots of different ways that you can do this. I'm going to start off by talking about non-conservative. non-conservative order parameters. So for instance, let's say you have a two-phase system, right? So you have your eta goes from omega to, let's say, 0 and 1. There are all different kinds of different conventions. You may pick 0 to 1, you may pick -1 to 1, you may pick -0.5 to 0.5. It really doesn't matter. You can pick it to be whatever you want as long as you use it, as long as you design it consistently with your free energy. So then the idea, of course, is that you have a domain and you define your geometry implicitly. So in this region here, this white region, eta is equal to 1, and in the black region, eta is equal to 0. Right? I grabbed this figure from Wikipedia. They use phi, lots of different conventions. I use eta, but that's the general idea, right? So two-phase system, you might have a multiple phase system. So a multi-phase system. And lots of different ways of doing this, but one way is to use a multi-phase field variable. So in a case like this, you would have a vector valued order parameter, and each component of the order parameter would correspond to one individual grain. I do a lot with microstructure evolution, and so this picture, again, from Wikipedia, does a pretty good job of illustrating how this works, right? So like this grain here is eta 1, this grain here is eta 2, and eta 3, and so on, right? And you just construct your system such that eta is equal to 1, and exactly one of the etas is equal to 1, the other etas are equal to 0, right? You can also use, there are other ways you can model systems like this. I just put the KWC method in here because that's an alternative to this kind of modeling. If you're looking at modeling microstructure evolution rather than modeling one order parameter per grain, you can use like a orientation field theta, which goes from omega to SO3, and then a disorder parameter, which goes from omega to 0 to 1, and this tracks losing my marker here, this tracks the orientation, and this tracks the disorder at each grain. And one of the advantages of using a KWC type model instead of a multi-phase model is that with KWC, you only ever have to track two fields, whereas with a multi-phase field type model, in principle, you have to track in order parameters for in grains. And if you're working with thousands of grains, of course, it's not tractable. Usually you can get around this by using smart remapping. Like for instance, you can have eta 1 here and eta 5 over here actually be stored in the same field, and you just track that in this region it's eta 1 and this region it's eta 5. You can do all these things. It still can be cumbersome, and there are pros and cons to both cases. But one of the things that I want to point out here is that in all of these cases, our order parameter is non-conserved. In other words, if I take the norm of eta, or I integrate eta over the volume or the domain, it may change with time. All right, so my total amount of phase 1 may change with time. It may increase, it may decrease. But in many cases, we are actually interested in tracking systems that are conservative. Get a little space on the board here. All right, right, so if we have a conservative order parameters include, for example, species fractions. All right, if I am wanting to model a system that consists of 50% copper and 50% niobium, and I want to model the dissociation into two different species, well, my total amount of copper has to remain the same. My total amount of niobium has to remain the same, or whatever I'm working with, right? Unless I have an actual reaction function that allows me to move between the two, right? So if it's conservative, then that means the total amount of eta must be constant. Another example of a conservative field is if I have a design constraint. So maybe I'm doing topology optimization, and I constrain that my eta has to evaluate to a certain value. That's another example of a conservative order parameter. Another example is if I'm using a phase field to describe a crystal. So we'll talk a little bit about phase field crystal later on. But if in phase field crystal, I would have some constraint such that if I integrate eta over my domain, that has to equal the number of atoms in omega, and unless I have flux terms, that can't change, right? I can't just create or destroy atoms. The total number has to remain constant. So again, all we're doing at this point is we're just defining our order parameter, how our order parameter describes our system, and what constraints that order parameter has to satisfy. Excuse me. All right, and now we'll talk about the next part, which is defining the free energy. And this is, I think, where things get a little bit more interesting. All right. Now, I talked a little bit before about how we might define a chemical potential. So there are different and this is maybe the cooking aspect of a phase field model development, right? When we develop our phase field model, we want to figure out what physical phenomena will be contributing to our energy. What driving forces are going to move my system? So we'll start off with chemical potential. And this is usually something along the lines of a double well. Double well potential, and it might look something like this. W of eta is 1/4 1 minus eta squared. 1 minus eta squared times 1 plus eta squared. Right, where we have these basins of attraction, and you're just plotting this, it's going to look, something like that. Now, a lot of the time when you're working with a chemical potential, even though the implication is that you're actually modeling like thermodynamics, a lot of the time a chemical potential is used more as just a constraint, just to ensure that your eta, for instance, is attracted towards -1 or 1. Many phase field models work that way, but in some cases you may want to actually do thermodynamics. And one of the things that I think is neat about this aspect of phase field modeling is that you can attach some physical meaning to your chemical potential. Like for instance, one of the things we do is we look at deflagration of solid propellant, which is a chemical reaction. And so what we do is we figure out, or we decide that we're going to have some change in our energy from -1 to 1, and we can just use that to modify our chemical potential, right? And so now, this is still a stable point, and this is still a stable point, but there's going to be a driving force that pushes our solution from the unreacted state to the reacted state. Right? So that is one way that you can use the chemical potential for your benefit and actually trying to capture in more detail some of the thermodynamics of your system. Right. Okay. Now, what other kinds of terms are you going to have? We already talked about chemical potential, and we also already talked about gradient terms. Right, and a gradient term is typically going to look something like 1/2 kappa times epsilon maybe times nabla eta or gradient eta squared, right? And why is it that it's gradient of eta squared? Well, it makes thermodynamic sense. It's a good measure of how the energy is represented in the system, and it also has the attractive property that if we take the variational derivative with respect to eta, then we just get this nice kappa eta Laplacian, or epsilon Laplacian of eta. So you could certainly come up with other ways of including gradient terms or boundary terms in your model, but this one's very convenient because it happens to give you exactly what you're looking for. One question that can come up is, why did I put kappa and epsilon? A common thing that you'll see in phase field modeling is the inclusion of a length scale parameter, or a diffuse boundary. A diffuse boundary width. And your diffuse boundary width may show up here, and then it may also show up in your chemical potential, because it's often desirable to have your model set up such that as you decrease the diffuseness of your boundary, you converge to a sharp interface solution. And so that's one way of doing that. And I won't go into that in detail here, but you may see that out in the wild. Right? Another aspect of gradient terms that can often come up when looking at phase field modeling is anisotropic boundary energy. So anisotropic boundary energy, where you have some kappa that is a function of your orientation. And so if we have our order parameter here, I'm not scoring with markers today. So A is equal to 0, A is equal to 1, and then we have some normal vector here, where the normal vector is going to be equal to grad eta over the magnitude of grad eta. Then we assign some interface energy, kappa, that's a function of that normal vector. Right? And so, okay, well that seems easy enough to do. But then, of course, remember that back here we need to be able to calculate a variational derivative in order to get our boundary energy. And I'll talk a little bit about kinetic relations in a little bit. But it turns out that if you put in an anisotropic energy, then that's going to change your driving force naturally, right? So if you include a theta dependence or some eta dependence on your energy, right? In other words, you have some kappa that's a function of eta, then all of a sudden you're going to have to redo your variational derivative, and what you get then is kappa of theta times epsilon times the Laplacian plus, that's kappa double prime of theta times epsilon times k2, where this is the second principal curvature of eta. So what we have is this original term here, which is our curvature-driven flow. And then we have this term here, which is our torsion from interface anisotropy. There's a couple interesting things to point out here that this term is 0 if the interface is flat, which is one of the reasons why interfaces with boundary anisotropy tend to create facets. They tend to want to have flat interfaces as much as possible. Another thing for those of you who are doing grain boundaries, which I don't know how many that is, but if you have a double prime, kappa double prime of theta, then all of a sudden you run into trouble if your interface energy has a cusp at the bottom. And there are ways of dealing with that that I won't go into here. But the takeaway is that there's a systematic way of accounting for anisotropic boundary energy. And the last thing that I'll say on this is that this works well for weak anisotropy. In other words, as long as this is as long as this is relatively convex. But for strong anisotropy, needs regularization. So for strong anisotropy needs regularization. My mouse is getting in the way. Because if you have strongly anisotropic boundaries, then the minimum energy configuration is a faceted interface, and there's then no length scale. So you need to give those facets a length scale, and there's a couple of different ways of doing that. Again, kind of out of the scope of the talk here, but it's definitely doable, right? So now these are the two standard garden variety pieces of a phase field model. Let's talk about some of the other ones that you may see. Remember, all we're doing here is we are looking at how these different pieces of energy are represented in terms of the order parameter, right? So we have a system. Our system is defined implicitly through an order parameter. And now how does that cause our energy to change? So I'd like to talk a little bit about higher order terms. So we talked about chemical potential, gradient terms, but what about so higher order terms like this one, for instance? Consider this free energy functional. So integral over omega 1/2 eta times q squared plus gradient squared times eta plus 1/4 eta to the 4th minus epsilon eta squared. And this is actually called a Swift-Hohenberg equation. And yeah, let's talk about it a little bit. So this piece here is not too unfamiliar. This is our reaction term. Right, this is going to be what drives our eta towards 1 of 2 minima, right? But let's talk a little bit about this term here. This is our gradient term. And as you can see, it's substantially more complex than the gradient terms that we've looked at before. First of all, we have derivative raised to the 4th power, but then we also have this mixture of derivatives raised to the 4th power, 2nd power, and 0th power here. So what exactly is going on here, and what does this look like? How do we get an intuition for what this kind of energy would do to our system? And for cases like this, I think it's often useful to think in terms of the frequency domain. And for that, we'll make use of Planck-Charles theorem. So Planck-Charles theorem states that if take the norm of f squared, that's equal to the norm of f hat squared, where f hat is the Fourier transform of f. And this is a very powerful theorem. It tells us that the total norm of a function does not change when you take its Fourier transform. And we can actually take this theorem here and apply it directly to our gradient term here. You can apply it to the reaction term here as well, but right now let's just look at the gradient term for the moment. And if we move to the frequency domain, so Fourier transform making use of Planck-Charles theorem, then we have that this is equal to nothing other than integral over omega, or in this case, the real numbers, because we're moving to the frequency space, of 1/2 Fourier transform of eta, q squared minus magnitude of omega squared times Fourier transform of omega, or eta times d omega. Right. In other words, all we're doing is we're taking the Fourier transform of this piece here. It's actually a little bit more involved than that. You need to split it up and then take the Fourier transform of the individual pieces using Planck-Charles theorem. But you can kind of see that when you take the Fourier transform of this, eta turns into eta hat, and then nabla turns into norm of omega squared, right? Which is really what we're after here. Now, what does this do? How does this help us understand what is happening with our energy? And to do that, let's look at this graphically. So bear with me while I erase the board. The light board is great, but it is harder to erase. All right. This is getting a bit messy. There you go. Okay, so let's look at a plot of this in the Fourier domain. So we're going to look at a 1D version of our free energy in omega space. So if we take that component of the free energy that that we derived before, so put it up here, q squared minus omega squared, magnitude squared. If we're working in 1D, then we can just work with omega squared. And what we see is that, of course, this is nothing other than a double well potential, right? This is just a potential that has a minimum at minus q. That's a q. And a positive q. Now, what we're interested in, of course, is our k multiplied by our eta, right? You remember we had eta hat times k hat times eta hat. That is our free energy, right? So what if I put some eta in here, what does my free energy look like? Well, if eta is equal to 0, that's obviously going to give me 0. 0 all the way through multiplies through to 0. Fine. But remember, we talked about how you may have a constraint on your order parameter. You may desire that your order parameter have a norm of 1. Using Planck-Charles theorem, because if it has a norm of 1 in real space, it must also have a norm of 1 in Fourier space. So let's just give it a very small value that integrates to 1. So I'm just going to put it all in here, and then all of a sudden we see that, oh, if I give it a small value out here, it's going to produce this large value. So this yellow region corresponds to eta hat times k hat, right? That is blowing up our energy. So what are we going to do? Well, clearly the thing to do then is to localize, right? And we want our eta to be as far away from this high k region as possible. But if eta is just centered around 0, we're still going to have a fairly large region in here that is non-zero. So what we can do instead is we can move it over to this minimum here, we see that our yellow region is getting smaller and smaller. We can squeeze it, and it gets smaller still. And we can also put it at the negative value as well as the positive value. And you can see that as we approach a Dirac delta in each of these cases, we're going to end up with the global minimum of our energy, subject to the constraint that the norm of eta is equal to 1. Okay, well that's useful. Now that we understand what our minimum looks like in Fourier space, now we can look at what it looks like in real space. If you have a peak at plus or minus omega, where omega is equal to plus or minus q, well, if you take the inverse Fourier transform of that, that is nothing other than a sine wave that has frequency 1 over q. And remembering that we do have a double wall potential, our amplitude is controlled by the chemical potential. So this is interesting. Whereas before, our minimum energy case is always going to be kind of as simple as possible. In a sense, when we have this higher order term, now our minimum energy case is as complex as possible, or as high frequency as possible. And this leads to interesting models for things like phase field crystal or small like rod and tube type microstructures. So we'll circle back around to that. Again, please feel free to stop me in the chat if you have any questions. All right. What are some other ways you can include physics inside your chemical potential or inside your free energy? Some phase field models include non-local terms, and by non-local here I just mean that it depends on a global solve, so that may not be quite the right way to describe it. But like, let's say for instance that in addition to having a order parameter that evolves, I also have mechanical load constraints on my system, and I know that my modulus inside this region is going to change in order to minimize not only the chemical potential and the gradient terms, but also the mechanical energy as well. So I can add to my chemical potential in the following way, and we'll assume for right now that I'm working with different etas. So I'm using a multi-phase field model. You can certainly construct different varieties depending on the kind of order parameter that you're using. But our non-local terms here would be sum over omega gn of eta n times u n of grad u, where grad u is the displacement gradient. And so this is actually pretty easy. This here is just a mixture rule. So it can be as simple as just like a volume, weight by volume or weight by area mixture. And then we have a free energy density here, and all we're saying is that, well, our energy is going to be dependent on which phase field model or which order parameter is present under which displacement gradient. Of course, the catch here is that in order to actually faithfully represent this, you're going to have to solve the problem of u equals to arg and u subject to boundary conditions f right. In other words, you're actually going to have to, at every time step, or nearly every time step, solve a mechanical equilibrium problem where the constitutive response is governed by eta. And so you have this tightly coupled interaction between your etas, which respond in order to minimize free energy, and your mechanical response, whose constitutive behavior is governed by those etas. Now, there's lots of different ways you can do this, and actually there's some really incredibly fast ways of calculating the mechanical response, especially if you're working with frequency domain methods or spectral methods. Won't get into those here, just so you know what's possible. Another kind of free energy that you might include is like a constraint. A constraint term. So for instance, let's suppose that I want to require that, let's say I want my eta to evaluate to, we'll call it C naught. So this is like a specified value. You can think volume fraction. All right, so it's a specific value. How can I add a energy term to my phase field model that encourages this constraint? As we talked about constrained order parameters. Well, one thing I could do is I could just add the following. Right, where eta is nothing other than the total integral of eta. And in this, oh, I forgot to add a lambda here. Lambda over 2. So what I'm doing is I'm adding a energy term, and I'm letting the energy term kind of grow in an uncontrolled manner. The only way that I can cause the energy term to not grow in an unbounded sense is to actually have eta be equal to C naught. So that if I take this and plug this into my my free energy and I calculate my kinetic relations, then I've got this lambda here, and I can tune that lambda to determine how much I want to enforce this constraint. So in some cases, this is a really nice and easy way to enforce a constraint, or something like a constraint in a more of an implicit way. And sometimes it even has advantages, like maybe your maybe it's that your order parameter is mostly conserved, but there's a little bit of wiggle, right? It can squeeze or expand, and in that case, lambda would actually correspond to like a constitutive response of that behavior. So again, to some extent, this is like cooking, right? Where we're saying, oh well, this would sort of give me the behavior that I want. And as long as I understand the way that it gives me the behavior that I want, then I will get controlled behavior in the end. Oops. All right. So there are lots of different kinds of energies that can be included in a phase field model. There are, lots of different kinds of ways you can include energy. We certainly can't go into all of them right now. But hopefully this gives you an idea of how you can kind of intuit, generally, if you have a free energy functional, what is that free energy functional going to have on your ideal solution? And so now let's talk about the final piece of the phase field theory, which is looking at kinetic relations. And to me, actually, this is one of the pieces that is maybe a little bit the most daunting, because how do you get from a free energy to a I see there's, okay, thank you. There's a question. How do we know lambda is correct? Yeah, that's a great question. It's kind of up to you. I would say if it's a hard constraint, so if it's absolutely true that your constraint must be satisfied, then I would say you know that lambda is correct if the constraint is satisfied to a satisfactory tolerance. Like let's say my eta has to have a norm of 1 plus or minus 10 to the minus 8, for instance. Well, in that case, when you're evolving your order parameter, then you need to make sure that lambda is large enough as you go to make sure that you are always satisfying that constraint. And if you're not satisfying that constraint, then you need to continue to increase lambda. And by the way, that's no worse than using an explicit method or any other numerical method that includes error. You're always going to have an accumulation of error. One of the nice things here is that you can always control that error with a very definite knob. Another way you can know that lambda is correct is if you actually interpret your constraint as like a constitutive model and like a bulk modulus. In that case, yeah, you can actually look at it and say, well, my lambda is controlling a constitutive response in my system. So, well, this is kind of getting hazy up here. So. All right. Thanks for the question. Okay, so now talking about the kinetic relation. There are basically two kinds or two families of kinetic relations that you can have in a phase field model. And so I'm going to talk about both of them here. The first one that I'll talk about is what are called Allen-Kahn kinetics. And Allen-Kahn kinetics are non-conservative. So it's going to be the most simplistic of different kinds of kinetic relations. Now, I think that it's useful to think of this in terms of, rather than eta as being a whole function, let's think of eta as being just like a 2D vector. So I'm going to let this be my eta. And in fact, I'm going to say this right here is going to be eta 1, and this right here will be eta 2. And eta is not a function here, it's just a like x1, x2, right? It's just a 2D domain, okay? Now, when I am modeling my system then, my free energy I can think of as like a set, or like a function that's defined in 2D space, right? Where the minimum is, of course, going to be right here-ish. Now, if I'm setting up my physical system and I have a state, maybe the state is right here, right? How do I model the evolution of this system? Well, the idea behind Allen-Kahn kinetics is nothing other than gradient descent. I'm going to take my vector and I'm going to move my vector in the direction that corresponds to the steepest gradient, right? So right here, actually let me switch to a different color so it's a little more visible. Right here, that's my gradient right here. That's my gradient, right? I start out here, that's my gradient, and so on, right? And this gradient is nothing other than dF. If I'm going to call my free energy F, then this is nothing other than dF by d eta. Remembering that d eta is eta 1, eta 2. We're not thinking of it as a function just yet. And actually, I wasn't quite right here. This is not dF d eta. It's actually negative dF d eta, right? I want to go in the direction of my minimum energy, not my maximum energy. Okay, well, so then if I want to actually set this up as a mathematical model, then I just have d eta by dt is proportional to minus dF by d eta. My velocity is proportional to the direction of steepest descent. Well, that's pretty easy. And what I typically do then is I just say this is equal to L times dF by d eta, where L is some mobility parameter. The idea behind Allen-Kahn kinetics is that we're going to do this exact same thing, but instead of a 2D gradient, we're going to replace with a functional derivative. Okay, so just a quick recap on what the functional derivative is. It's usually defined this way, df by d eta times c dx is equal to the limit. Markers are failing me today. Limit as epsilon goes to 0 of d by d epsilon f eta plus epsilon c. So this is the functional derivative, or the Gateau derivative, or the directional derivative, right? And it's a derivative of a function with respect to a function. It's a derivative of a functional, in this case free energy, with respect to a variable that's actually a function over in the overall function space rather than just x1, x2, right? And so we can think of, if this is my eta, now we're thinking this is abstract eta space. What I'm wanting to do is I take eta here and I pick some direction, c, and df by d eta tells me how much does my function change in that direction, right? This projects the change of my energy onto that direction. And so I can look in all different directions. Right here, I'm looking in all different directions, and this piece, this final derivative, is going to be the direction in which my function moves. Okay? Now, I'm not going to go through how to calculate variational derivatives. Again, I assume that that's something that you're already familiar with. If you've taken calculus variations, you'll know what that is. The bottom line is, this you can almost always calculate. It may be messy, but you can almost always calculate it for any reasonable free energy, right? And so then if we replace this with our functional derivative, what we have is d eta by dt is equal to minus L delta f by delta eta. And these are our Allen-Kahn kinetics. This is our Allen-Kahn kinetic equation. And again, you can just think of this as nothing other than gradient descent. I'm going to always be nudging my solution along in the direction that minimizes my free energy. Okay, so then as long as you understand the free energy functional, you understand the direction in which your energy or your order parameter is going to go. Now, I think that one's relatively easy to understand. The other type of kinetics that you will frequently see are, let me erase the board here. Yeah, the other type of kinetics that you will frequently see are called Cahn-Hilliard kinetics. And Cahn-Hilliard kinetics are conservative. And I just have to be honest and say, when I first encountered Cahn-Hilliard kinetics, I really had no idea how this could be possible. Right? How is it that you can derive a governing equation that is going to be conservative, that causes your eta globally to not change? It just doesn't seem possible. And in fact, when I was doing some research for this lecture, I found that the derivations that I found, at least, are kind of confusing and somewhat ad hoc. They typically go along the lines of something like, well, we want our order parameter to evolve according to a flux, because if it evolves according to a flux, then it will be conservative, or the divergence of a flux, then it will be conservative, and we're going to pick our flux to be the variational derivative of the energy. And to me, that's fundamentally unsatisfying. So I'm going to give you my best shot at showing why Cahn-Hilliard kinetics is conservative and how we derive the conservative form. So let's start just by looking at this graphically. So we'll go back to our eta space here, and we're going to redraw our free energy functional here. And Excuse me. Okay, so back to our free energy functional, and now our minimum is still here, right? But we're no longer allowed to freely traverse eta space. We are now constrained. We are now we're no longer able to just move any direction that we want. So let's say, for instance, that we start here at this point. Well, if we start here at this point, I'm going to impose this constraint that eta 1, the one norm of eta is equal to constant. In other words, eta 1 plus eta 2 has to always equal to, in this case, 1, or whatever it started out with. This is actually a fairly reasonable interpretation of the conservative constraint, right? Because if you sum up all the components of 1, then you get the same value. Just like if you sum up all the integral of eta, then you get the same value. But so now, if we're constraining ourselves so that we're only allowed to move along this line, then our solution is going to look more like this. We're going to move along the line until the point where we're at the smallest energy we can possibly be without leaving the line. And okay, so that's fine. I mean, we can understand that this is happening, but how do we actually derive this in a functional derivative sense? So for that, I want to go back to this idea of the functional derivative. And let's say we have our d by d eta, or epsilon. So and this is f of eta plus epsilon c. And we're going to take the limit as epsilon goes to 0. Okay? And I want to revisit this idea of what xc is. Right? Before I just said, well, we're at this point here, and xc is any admissible search direction. Right? And if you've taken calculus of variations, you know that xc has some constraints on it. It has to be admissible. In other words, for instance, it's not allowed to alter essential boundary behavior. So it has to be 0 at the boundary. It's not allowed to push the solution in any of those directions. And I want to generalize this to think about, epsilon, or xc in this case, is any direction in which we're going to allow our solution to move. Okay, so whereas before we allowed our solution to move any direction that we want, now we're going to only allow our solution to move along our constraint line. Now, our xc is going to be snapped to our constraint. We're only going to be able to move back and forth on this constraint, and that will restrict our variational derivatives so that we don't wander off into a region where we no longer change our value. And so then, that's all well and good. Now, how can we find xc such that the norm of eta does not change? How can we find xc such that the norm of eta does not change? Well, if xc is such that the norm of eta does not change, then we know that d by d epsilon of eta plus epsilon c dx as epsilon equals to 0 must be equal to 0. Right? Fair enough, right? And in other words, I cannot change my total value, right? This total value here has to be the same. If I add epsilon c to eta, it still has to satisfy that constraint. Which really, this is actually as simple as saying, well, in other words, the integral of xc must be equal to 0. This is actually a very easy derivative to calculate, right? Epsilon only shows it here. There's no derivatives or anything. In other words, all we're saying is that xc itself must have 0 integral. Our variation must have 0 integral. That's it. As long as we add a 0 integral variation, then our constraint will be satisfied. But then the question is, well, okay, that seems like a tall order. How can you guarantee for sure that c has your integral? Well, what we can do is we can say let c equal to minus the Laplacian of phi for some function phi. If c is equal to the Laplacian of phi, then if I calculate integral of c dx, well, that's nothing other than the integral of del dot grad phi dx. And now I can use the divergence theorem just to get that this is equal to integral of n dot grad phi dx. And I'm just going to say for right now, we're going to let that be equal to 0. In other words, we're going to impose boundaries such that we have no flux at the boundary. So, like, let's say we have Neumann conditions at the boundary. If we have Neumann conditions at the boundary, that's going to be satisfied. If we have periodic boundaries, that's going to be satisfied. It's actually pretty easy to satisfy this constraint. As long as we satisfy this constraint, then this, we have just shown that this is equal to 0. So, as long as c is equal to the Laplacian of phi, then I know for sure that it will be volume preserving. And now you may be wondering, well, that sounds good, but how do you know for sure that this will capture every possible volume conserving c? Basically, how do you know that for any c there exists a phi such that c is the gradient of, or the Laplacian of phi? And for that, I'm just going to really quickly say we know that the Laplacian of phi, or the Laplacian operator, has only one zero eigenvalue. That one zero eigenvalue corresponds to translation by a constant. Every other eigenvalue is non-zero, which means if you remove the variability, so like if you restrict phi to having a constant value, then the Laplacian operator is in fact invertible. And then you can guarantee that c, for every c, there's an appropriate phi. Maybe that's not satisfying, but at the very least we know that if phi exists, then we will have a c that satisfies our admissible variation. Okay. And now we get to the cool part. I'm going to take c and I'm going to plug it into here. I'm just going to keep my illustration here and finish the analysis on this side of the board. Right, so now I've got my my same functional derivative here, and what I'm going to find is that my d by d e f eta plus epsilon c for c equal to grad phi, where now we know c, equal to minus Laplacian of phi. And by the way, it's minus Laplacian because minus Laplacian is positive definite. Yeah, that's all I'll say on that right now. But what we see then is that if I take this and I do my same usual calculation, right? I take my derivative inside the integral, I do the chain rule, I do apply boundary conditions, etc. Then what I end up with is nothing other than delta f by delta eta times c, but now c is equal to minus Laplacian of phi. So I'm going to put minus Laplacian of phi dx here. Okay, and now we come to the final step. Because all we have to do at this stage is realize that we can take this Laplacian, apply the inverse product rule, and the divergence theorem, and we can actually move this Laplacian right over onto the variational derivative itself. And so what we get then is minus, actually I'm going to put it like this, minus Laplacian del f by del eta. dx. And this is our new modified constrained functional derivative. Our modified or our constrained functional derivative. There's some fancy mathematical ways of referring to this. Sometimes it's called the H inverse gradient descent because it's technically dual to H1 space. I think it's easier for me to just think about a constrained functional derivative. And so if this is now our constrained functional derivative, then our governing equation is nothing other than d eta by dt is equal to L times the Laplacian of df by d eta. So if this is the Laplacian of df by d eta, then we know for sure that this will be conservative. So hopefully that's satisfying to you. To me, that's the easiest way to think about it. But just in case you don't believe me, we can prove again really fast that this thing is conservative. And we can do that by the following. I'm going to calculate the derivative of d eta by dt dx. I'm going to integrate that over omega. And I'm going to, let me start here. I'm going to calculate the time derivative of eta dx. And if this is constant, if eta is constant, then this should be equal to 0. This is equal to integral over omega d eta by dt dx. And we know from our constitutive relation that this is nothing other than L omega del dot gradient delta f by delta eta dx. By the divergence theorem, we know that this is equal to L integral over boundary over omega in dot del df by d eta. And if we have appropriately defined boundaries, this is equal to 0, showing that it is in fact conservative. If you don't have inappropriately defined boundaries, then your total volume changes based on the flux. And the flux is just defined here. So hopefully that helps make some sense. And we will be exploring how Cahn-Hilliard kinetics works in a couple of practical applications going forward. The last thing that I want to just put a little teaser out there for is nonlinear kinetics. Both Cahn-Hilliard kinetics and Allen-Cahn kinetics are linear, right? Kind of by inspection. The variational derivative is linear, the Laplacian is linear. So you're always going to have this linear relationship. But there's no reason why you can't have d eta by dt equal to some arbitrary function of df by d eta, right, where g is some nonlinear response. And actually, some work that we've done and also some work that Dennis has done over the past couple of years have really shown that you can really get some interesting and very physically meaningful behavior if you consider nonlinear kinetics. I'm not going to go into that here because this is a basics of phase field lecture, but there are lots of interesting papers, and we'll even touch on a couple of examples that use nonlinear kinetics as we go forward. So with that, I'm going to erase the board. Give me just a second. Now, let's talk a little bit about numerical methods or computational methods. So actually solving these, deriving these equations is one thing, actually solving them can be something else entirely. So I'm going to start off just by talking about kind of the most basic way of solving one of these PDEs. So, and that's just the finite difference method. So this is kind of as, this is you open up MATLAB and you code it in about 5 minutes or so. Well, maybe not 5 minutes, but pretty quickly. The idea is that, well, you have a nice time-dependent first order and time differential equation, so you can just integrate that forward using something like the forward Euler method, and where you calculate spatial derivatives using some kind of central difference scheme. And that's really very easy to implement. And one of the nice things about phase field is you can get really interesting behavior just with a pretty simple implementation like this. But the advantages of the finite difference method actually go beyond just the ease of implementation. One of the nice things about the finite difference method is that you can use kind of arbitrarily complex boundaries because it's very easy to account for exotic types of boundary conditions. It's also relatively easy to merge together with other types of multiphysics applications. If you're doing fluids at the same time, or if you're doing electromagnetism, then it can be, no, that's not to say you can't do electromagnetism other ways, but it can be a nice, easy, and straightforward way of implementing this method. In my group, we use finite difference method all the time, actually, and we use adaptive mesh refinement, which, again, works really nicely with finite difference method, and we can actually do things like temporal subcycling to help adapt to some of the instabilities that can come from explicit methods. Obviously, of course, too, you wouldn't necessarily always use the forward Euler method. That's the easiest one to implement, but something like Runge-Kutta is going to certainly give you better stability, although explicit methods are always going to have some inherent instability associated with them. So on the subject of instabilities, that's the main issue with the finite difference method using explicit in time. It can be very slow, and in particular, it can be unstable for high order methods. So for Allen-Kahn, like if you just take your basic phase separation type phase field model for Allen-Kahn, then your time dependence, your time step is going to be proportional to your spatial resolution to the -2, which is usually not too bad. But then if you start adding higher order terms, like say if you're working with Kahn-Hilliard, then you're going to have at least 4 spatial derivatives, and then all of a sudden you've got x to the 4th, right? So, and then if you're using something like phase field crystal, then you'll have x to the 6th. So then all of a sudden if you refine your spatial resolution by a factor of 2, then you have to decrease your time step by a factor of 2 to the 6th, which just becomes absolutely untenable for these kinds of higher order systems. So what we generally do instead is we use spectral methods, especially for high order systems. I just want to really quickly derive for you how you would apply a spectral method in a 1D phase field model. So let's say you're trying to integrate d eta by dt is equal to dw by d eta minus plus d squared eta by dx squared. Okay, now rather than just integrating this explicitly, what we'll do is we'll take the Fourier transform. So if we take the Fourier transform, then what do we have? Well, nothing other than and this is the Fourier transform in space, not in time. So this is d eta hat, the Fourier transform of eta by dt, is equal to, this one's nasty because we've got eta squared, and those terms are really difficult to deal with doing Fourier transform. Eta squared is eta convolved with itself, and I mean, maybe there are ways of doing it that I don't know about, but it's if you're at least going at it from a fairly straightforward way, you might run into trouble here. So we're just going to punt, and we're going to say we'll put this off. It's just the Fourier transform of that stuff. And then the reason why we really like, or why we really want to do this method is because d squared eta by dx squared just turns into omega squared eta hat. Okay? Now let's do a expansion in time. So I'm going to let this be equal to eta n plus 1 minus eta hat n divided by delta t. So I'm going to do an explicit difference in time, and I'm going to write down the rest of this, noting that I'm indexing eta in terms of its either its current or its next value. So I still have my f of stuff here, dw by d eta, and I'm going to leave that at n, but my markers here are going to give me trouble, sorry about that. For this one, I'm actually going to use a semi-implicit scheme. So I'm going to let omega squared, or I'm going to let eta hat just be n plus 1. And the nice thing about working in Fourier space is that this is all just an algebraic expression, right? We don't have to invert any operators. So it kind of comes for free. Working with eta n plus 1 rather than eta n. If you're working in real space in an implicit solve, you got to do an implicit, or if you want to use an implicit method, you got to do an implicit solve. And so if we take this and we just rearrange it, then our final solution then is eta n plus 1 is equal to eta hat n minus delta t Fourier transform of this stuff, dw by d eta n, divided by 1 plus delta t omega squared for eta hat. So then if you want to actually implement the thing, what do? Well, you take your eta, do a Fourier transform of eta, and do a Fourier transform of this. So calculate explicitly, like do an actual forward FFT of dw by d eta to the n. Then once you have this quantity and this quantity, you can instantly update your eta n plus 1. And then in order, because we have this nonlinear term, then inverse Fourier transform eta back, plug back in, and then keep going back and forth. And again, I'm not going to say there aren't more clever ways of doing that. We actually don't use spectral methods a whole lot. So I'm surely missing out here on some more clever ways of doing it. But what you can see, or what maybe is hopefully obvious here, or apparent here, is that first of all, spectral methods make it really easy to do implicit time stepping. But more importantly, it makes it really easy to do high order methods. If I have omega squared, I have an omega squared for a second order in space method, but if I have a fourth derivative of x, then this is just omega to the fourth. A sixth derivative in x, this is just omega to the sixth. And it's still very easy to calculate. And it's, in fact, extremely fast. So, just a summary, advantages of spectral methods are that they are extremely fast for high order methods. They're extremely fast, especially for high order methods. When working with conservative quantities, you especially care about working with spectral methods are particularly valuable because otherwise you're really going to be killed by that time step limitation. I see. There's a question. Yeah, I think you're exactly right. So high order methods, and let me get to that question in a sec. Other really nice things about spectral methods are that they easily handle convolution. So if you have like interaction terms, non-local interaction terms, which are convolution in real space, that just turns into a multiplication in phase space, or not phase space, in Fourier space, which is really nice. Makes it really easy to calculate. There are also some really cool ways of doing implicit mechanical solves. Ricardo Levinson at Los Alamos just has some really amazing work on this, where they really like show how to do all kinds of cool mechanical solves all in Fourier space. So some really amazing things that you can do with that. To the question, excuse me, how do we know, or eta has to be periodic? Yes, usually. There are ways to get around it. They're kind of tricky though. I think to the best of my knowledge, if you want to use non-periodic boundary conditions, you have to kind of construct like internal boundaries that replicate the boundaries that you're looking for, but then still have that overall periodic domain be periodic. Because yeah, you're going to have to do a fast Fourier transform, and you've just got to be able to work in a periodic domain if you're going to use the fast Fourier transform. So yeah, I think that is probably maybe the biggest limitation of spectral methods. Also, to the best of my knowledge, they require full resolution in the entire domain. So if you've got a domain where you're only looking at a single boundary, yeah, that's to some extent a waste of computational nodes. You can't do adaptive mesh refinement in the same way that you can do with real space methods. So it may be, it's kind of domain dependent, and it's going to depend on exactly what what your problem of interest is. Another issue with spectral methods is that they can be more cumbersome to implement. Taking the Fourier transform of your free energy functional isn't always easy and straightforward. I think you can probably always do it, but it may make your code a little bit more difficult or a little bit more brittle to work with. So, but all that to say, spectral methods are amazing. You can do really incredible calculations in an extremely fast time. So, and thank you guys for the questions. All right, with that, I'm going to wrap up here just with the fun part, and that is phase field applications. All the stuff that I'm going to present for you today are various results that we've done in our group, some for papers, some that I just did for this class, and some that we have just posted online as examples. So I'll give information on how to find those at the end of the lecture, but feel free to poke around and take a look if you're interested in any of these particular things. So let's start just going back to our original example here. So again, for those of you who are really new to phase field, hopefully these equations make a little bit more sense. I want to give you hopefully a level of comfort with what phase field theory typically looks like. We look at this and we say, oh yeah, this is my free energy functional, I've got a chemical potential, and I've got a gradient term. I kind of know how that's going to try to minimize its energy. Oh, and this is definitely using what? Allen-Kahn kinetics, because there's no gradient here. This is just a straightforward variational derivative. Boom, there's my differential equation. And so then if I look at the result, excuse me, that's what I'm going to get. Okay, now let's move on to some more interesting examples. And to start with, let's look at spinodal decomposition. So spinodal decomposition is going to be, the free energy is going to be almost exactly the same as the free energy for the previous example, phase separation. It's just a chemical potential and a gradient term. What's different here are the kinetics, right? So you look at this and you say, oh yeah, this is a Cahn-Hilliard type equation, right? And so it's going to be conservative, right? And then this is going to be my final differential equation. And so let's start off by looking at how one of these systems evolves. And I'm just going to start off here with, I'm going to, in this case, let eta be -1 to 1. And I'm going to initialize my simulation with eta approximately equal to 0. So it's right there at the middle with a little bit of noise, which is what you see here. Now let's let the thing evolve. And sure enough, we see that as it evolves, the volume fraction of red versus blue is more or less constant. These things take a long time to run. If you want to see long-term behavior, you really need to do like dynamic time stepping in order to kind of accelerate, because as you can see, there's an initial transient that's really fast, and then well, it's just kind of poking along, so it takes a very long time before it really gets to a total global minimum. And by the way, one thing that I'd like to just comment on is stability of phase field methods, which I hadn't mentioned yet. But if you look at spinodal decomposition or even the previous method, what is the stable state? Well, the stable state for a non-conservative system is just going to be eta equal to 0 or eta equal to 1. Right? That's going to be absolutely as small as possible. For spinodal decomposition, it's going to be, well, consolidating eta equal to 1, consolidating eta equal to 0 with as little interface as possible. So kind of as boring as possible of a microstructure while still maintaining that required volume fraction. Now let's look at what happens if I start off with a slightly different value of eta. So I'm going to now start off with eta about, I think this is, eta is approximately equal to 0.5. So how does that affect our solution? And we see it struggles a little bit, and then eventually it's able to nucleate the second phase, and it's able to segregate the energy out nicely into its two different phases. And I think it's kind of fun to watch, because this is where you really see the distinction between Allen-Kahn kinetics and Kahn-Hilliard kinetics. In Allen-Kahn kinetics, a microstructure like this that we see here, well, all of those little bubbles would immediately collapse, right? Because if there's a ton of curvature, it's going to go to 0. With Kahn-Hilliard, you can't just delete all of these bubbles. It has to find some way of moving all the eta equal to 1 or equal to -1 phase together. Now, we'll say one comment about conservative kinetics, especially the kind of conservative kinetics that we see here. Just because the kinetics are conservative doesn't mean they're locally conservative. They're globally conservative, not locally conservative. That means that it's possible to go from a situation like this to a situation like, oh, yeah, that didn't quite work out the way I wanted it to. Let's say, make this really small. Right, this is called Ostwald ripening. It's possible for mass to just sort of disappear from here as long as an equivalent amount of mass appears over here. So that's one thing to watch out for if you're working with conservative methods. That just because it's technically conservative over the entire domain doesn't mean that you're necessarily going to get physical behavior from a conservative standpoint. Nevertheless, it's still kind of cool to see, and a lot of the time you do actually get interesting and relatively physical behavior. Actually, there's some great videos on Wikipedia that show Ostwald ripening and behavior that's very, very similar to this. You actually see bubbles that change size, and you can't really tell how the mass is getting transferred, but it's captured really brilliantly with Kahn-Hilliard kinetics. So let's switch gears, and we'll look at something a little different. This is a Swift-Homburg equation, and we actually talked about this before, right? So this is that higher order gradient term. This is that term that gives you a double well potential in the frequency domain, and these terms over here are nothing other than our double well potential in the real space, and then this down here is nothing other than the expansion of our governing equation. And again, what I hope that you get out of this is you can look at this and not be daunted by all the math, because all that it really comes down to is identifying what are the different pieces doing to my physics, and how do those different pieces affect the evolution of the system. I don't really do phase field crystal. I actually just implemented this for this class in our code. But it's kind of fun because I knew what it was, but I never implemented it myself before. But let's say we want to evolve the system, and I'm going to start it off at, so eta will again be in -1 to 1, and I'm going to start off with norm of eta equal to, I think it was like 0.67. I need to actually double check that number, so don't quote me on it. It is on our on the regression test that's online if you want to check it out. And so what's going to happen? remember, this is going to favor high frequency terms, and it's also going to require that this total amount of eta be the same. So there's like, what, 0.67 atoms inside our computational domain. So when we run it, boom. And it's really amazing to me how fast it converges to this solution. It really is only just a couple of time steps before you start seeing these crystal patterns emerge. And we could spend a lot of time talking about this phase field methodology, and you can actually see like, oh, there's like grain boundaries, you can see defects, you can see a microstructure evolution. You can do some really amazing things. Like you can apply stress and measure Young's modulus, or you can model grain boundary evolution. Really a lot of amazing possibilities, and this is just like the very basic vanilla version of phase field crystal. There's all kinds of developments that have happened over the past 20-ish years or so, where they've really been able to model all kinds of amazing behavior. I will just point out that this is really kind of a heuristic equation. This is sort of a, well, we want an equation that will give us a high frequency term, and we know that this is about the packing factor for hexagonal lattice, so let's see if it gives us a crystal, and sure enough it does. I think there are ways to make it a little bit more physically informed, but at the end of the day, a lot of this really does come down kind of to cooking. And so just again, don't be too intimidated when you see this stuff, because a lot of the time it just comes down to what is your intuition and how are you going to use your intuition to model your problem. Now, what happens if we change our eta, our original value of eta? So I'm going to let now eta equal to 0. So remember, we're going between 1 and -1. And if this were in person, I would say, what do you think is going to happen? I thought it's really interesting. What you end up seeing is this kind of cool behavior here. You see these rod-type structures forming. And you can see that, yeah, this is doing a pretty good job of matching this like equal distribution of plus and -1. Whereas the crystal structure is more faithfully matching this type of packing factor, right? There's a lot less red than there is blue. Here, there's about an equal mixture of red and blue. As you watch these things evolve, you can see defect evolution. You can see microstructure change. Again, lots of cool stuff here, and lots of work that's been done to apply these to lots of cool different systems. My goal here is just to give you a taste so that you know what's possible. All right. Another common use of phase field methods is in growth of dendrites, so for solidification. And let's look at what this equation is doing here. This is our actual phase field evolution equation. And you'll see the usual suspects. We've got our gradient term here, and then we have a chemical potential term here. But we've modified this a little bit. Specifically, there's now a term here that is dependent on grad eta, which is an anisotropy term. So now we're going to give this thing three-dimensional anisotropy that's dependent both on the orientation of the interface, but then also on the temperature. So this is in addition to modeling eta, we're going to be modeling temperature. And even with a fairly simple dendrite growth model, you can get some really cool behavior. We're looking at the growth of the dendrite colored by temperature. And you can see that this anisotropy plus coupling to temperature gives you this really interesting kind of exquisite patterning that is really representative of a lot of the kinds of solidification behaviors that you see. Again, this is actually a kind of a first implementation of dendrite growth. The modern dendrite growth models are much more complicated, but also more difficult to present in a class setting. So if this is something that's interesting to you, there's lots of great papers that I can point you to. Something that's a little closer to home for me is looking at multi-phase field modeling of microstructure. We talked about this before, right? We have our phase field model, or a chemical potential here, and this chemical potential is constructed such that it's minimized when exactly one eta is equal to 1, and all the other etas are equal to 0. And if you really want to, you can go prove that to yourself. It's not hard to do. Maybe it's just a little bit tedious. But then if you take this as your free energy and then plug that in plus just a basic gradient term and use, in this case, Allen-Kong kinetics, because we don't care about grains being conserved as long as we're not changing species, then we are able to run some pretty cool results here. So I think in this case we have like 100 grains in 3D, and as you can see, the microstructure continues to evolve, and it's just driven by interface energy. Again, one of the cautions I'll give you on using models like this for modeling microstructures is that a lot of the time this isn't really how microstructure evolves. This is like soap bubble dynamics, and really you want to look more at microstructures that include anisotropic boundary energies, and anisotropic mobility parameters and shear coupling. It's really much more complex than this, but this does a pretty nice job of demonstrating the capability of phase field method to capture these kinds of problems. And by the way, just a comment on performance time. Pretty much everything that I've shown here runs on the order of minutes. I think that the longest simulation that I've shown you, or that I'll show you, is still less than an hour. With modern computational techniques, it's really amazing what you can do, even with these methods that are relatively historically expensive. A common application of phase field method is to fracture mechanics. I have to be honest, I'm not really a big fracture mechanics person. We have some papers on it, but I know the theory, but it's never been my main focus. I'm just going to kind of present to you, here's the equations of fracture mechanics, and you can see, we've got kind of our usual suspects here. We've got our, I think this is one time we call it C instead of eta, but we have a phase field that corresponds to our crack propagation. Right? This is an example of a phase field evolution that is going to be strongly coupled to mechanics. In fact, mechanics is going to be by far the dominant driving force in fracture, kind of for obvious reasons. And so because of that, the mechanics plays a very strong role in that driving force. And I wasn't able to get the free energy formulation for you here, but there are numerous papers on this that you can look into if you're interested. We have our gradient term here, and we have some other various terms that control different aspects of the behavior. But when you do fracture mechanics, you can, one of the really nice things about the phase field method is that you don't end up with a lot of the mesh dependence or artificial length scales that you can get with other types of computational fracture. This is from a paper a couple of years ago. This is a very recent result from my colleague Banana Markwell at Los Alamos National Lab, just demonstrating the capability of the phase field fracture mechanics method. So, and I will mention here too, I think it's actually not as visible as I was hoping it would be. Adaptive mesh refinement is really comes in handy here. We use Banana's adaptive mesh refinement and Alamo to capture this complicated geometry without breaking the bank in terms of computation time. Another fun application of phase field is to topology optimization. I'll just give a caveat here. Phase field, I think, is not necessarily the best way to go when doing topology optimization. There are a lot of problems with it, but there are some problems in topology optimization that you can solve correctly with phase field, and so I'll present one of them to you here. Let's talk a little bit about what this. Let's talk a little bit about what our free energy looks like. We have a free energy that consists of, first, this is our chemical potential, and then we've got our usual gradient term. And then over here, we have a mechanics driving force. So this is mechanics. And right here, we have our constraint. Right, so this is the target volume fraction, right? And so I think there was a question earlier: how do we know what lambda is correct? Well, in this case, because we're not applying a constraint in order to satisfy physics, we're applying a constraint in order to satisfy our design, which means there's some flexibility. And so this is one case where a constraint method for applying conservation of eta is actually maybe a little bit advantageous because it allows us to kind of tune and control that value and how rigidly that value is constrained. But once we have this as our free energy, this is just our standard Allen-Kahn driving force. Now, we're doing topology optimization, so there's no real meaning to having a driving force, right? This is really just using a gradient descent as a numerical optimization technique. So if we take our box here and we're going to say V is equal to, I think, 0. Is equal to 0.1. So I think it's about 10%. And then along the edge here, we're going to apply. We're going to apply a fixed boundary constraint, and then over here, we're going to apply a load. So those are our boundary conditions. Now note our boundary conditions are communicating to the phase field through this mechanic solve. Right? So the mechanic solve causes the driving force near the high concentrations of strain energy to be higher, and then it drives the phase field towards that direction. So if we let the thing run, we see that sure enough, we get this nice truss structure, which is sort of a well-known benchmark problem in topology optimization. So you can do this in 3D as well. And again, like I said, there are limitations when doing optimization or topology optimization with phase field, but it can be a good way if you're looking at if you're wanting to look at design of optimal microstructures. Okay, I talked a little bit about microstructure evolution before, and we're getting into some of the specific applications that we use in my group quite frequently. This is our group's method for grain boundary migration or microstructure evolution in polycrystal materials. This is our usual chemical potential. We have our usual anisotropic boundary term. We have a second order regularization term. I talked to you about that a little bit before because we're interested in capturing grain boundary faceting. So we have to include that as well. And then we have our energy driving force also. This term is a nonlinear kinetics. A nonlinear kinetics term, which actually reduces down to just a thresholding term, which is fairly easy to, relatively easy to implement. And then this last piece here is a nucleation term that we use to perturb boundaries specifically in accordance with temperature and local driving force. And so I won't go into great detail and all this stuff because it's getting kind of out of the scope of a basic phase field lecture. But some of the stuff that we like doing here are looking at faceting, boundary control phenomena, looking at things like boundary twinning. This is spontaneous twinning, and a more recent result is this hierarchical twinning that we started to see using this nonlinear kinetics and phase field driving or plastic flow method for incompatible boundaries. So, and then the last example is the reason why I include this example is because I know that this class is looking specifically at proposal writing in solid mechanics, and this is kind of my experience here is that I took what I knew about phase field modeling and applied it in a new area. And interestingly, even though phase field is really well known in solid mechanics and material science, it's relatively unknown in many other branches, including energetic materials. So we took this phase field model, and actually there are several iterations of the phase field model. This kind of summarizes the model as it is now. I'm not going to go into it in detail. There are papers on it if you're interested. But we can do things like looking at a solid motor and seeing how the solid motor burns through time, and capturing this really interesting burn surface. And we're also very interested in looking at so we're capturing the flow of or the regression of the interface, but then also as the interface is moving, seeing how the thermal and mechanical loads affect the stress state inside the propellant. So a lot of this stuff is stuff that is really a perfect match for phase field. And there are lots of different types of applications out there for phase field. There's lots of low-hanging fruit, I would say. So, and the last thing I'll just say is beyond solid mechanics, some of the things that we've applied phase field to. Again, it's kind of unlimited how many ways you can use this technology to, or use this framework to look at really highly complex physical mechanisms. This simulation here is a recent one under review, where we're looking at flow through a porous medium. Over here, we have water droplet impacting on wind turbine blades. We have flow field resolved dendritic growth. And then over here, we have a phase field described constraint that produces this shock in our flow here. So anyway, lots of cool stuff, and I will leave it there. So thank you very much for your attention and for your questions. I will just put this information here. For further information, my group's website is solids.group. I think I said all of the simulations that I presented here are done using our group code. So our group code is called Alamo. And it's open source and we have documentation online, so feel free to check that out. Many of the examples that I presented are actually our regression tests in Alamo, so you can actually go and get instructions on how to reproduce those tests exactly. I'll also post notes online, solids.group/teaching, and then finally, feel free to just reach out to me directly by email, breynolds@iowastate.edu. So again, thank you very much. I'm going to just pause here and wait for about 30 seconds to see if there are any questions, and then beyond that, I'll just work with you guys to set up virtual office hours for question and answer later. Thank you very much. All right, I think we've passed the line, so I will just wait and chat with you in office hours later. All right, thanks again. Bye.